Welcome back to the Deep Dive. Now, if you're tuning in, chances are you already know the big names in precision force measurement. Interface, for example, it's pretty much synonymous with those standard, really robust load cells and torque transducers you see everywhere.
Absolutely. They're the backbone in so many industries. And that familiarity is important, actually, because today we're kind of pushing past that idea of standard.
Going beyond the catalog, so to speak.
Exactly. Well, those standard products are great. They work perfectly from those things. We're focusing today on that, let's say, critical 10% of projects. The ones where the real world throws engineers a curveball that an off-the-shelf part just, it can't handle it.
Okay.
So yeah, our mission today is to unpack why that complexity really demands fully customized solutions and how expert teams actually deliver that specific precision without losing accuracy.
That's a fascinating gap you mentioned. You could have a standard load cell technically rated correctly, but the place it needs to go. Maybe bolted deep inside some proprietary machine on an oil rig or needing to be tiny for a surgical robot. It just won't fit or survive. You need something totally unique.
That's the heart of it, really. Standard products are built for, standard conditions, general utility. But these high-stakes applications, they often come with unique, non-negotiable constraints.
Constraints that aren't just about the measurement itself.
Right. If your sensor can't physically fit where it needs to be, or function reliably in that specific spot, or crucially survive the environment, the measurement data is useless, isn't it?
So let's dig into those specifics. If we assume the basic function measuring force or torque is understood, what are the variables that really push a project over the edge into that custom required zone? It must be more than just needing a slightly different capacity.
Oh, definitely. It's usually a combination of things. Probably the most common is just the physical geometry. A unique shape, maybe an extremely tight form factor, something you just can't buy off the shelf.
Like needing it to be much smaller, or a weird shape to fit around something else.
Precisely. Or you might need non-magnetic materials, for instance. Or maybe a really specific capacity that's an outlier, like, say, a tiny 3-pound capacity transducer that has to fit into a space originally designed for a 50-pound unit. That happens.
And you mentioned survival earlier. It sounds like the environment itself can often be the deal breaker for standard instruments.
Without a doubt. Environmental survival it's huge. We see requirements for everything. Think cryogenic temperatures for space simulation chambers, or the opposite, extremely high temperatures inside engine test cells.
Wow, okay.
Or maybe it's about chemical resistance, continuous exposure to harsh stuff, or protection against really high vibration environments where normal cable connections would just fatigue and fail.
So that might push you towards something like wireless.
Exactly. That often requires integrating custom wireless communication right into the sensor assembly itself. You just can't risk a cable failure.
Hearing all that, the custom solutions team sounds less like they're just tweaking existing parts and more like an essential engineering partner, almost a safety net.
That's a good way to put it.
Yeah.
They really act as that bridge, working directly with the customer's own engineers, their testing groups, to fully define all those constraints up front.
So they spend a lot of time just understanding the problem first.
A significant amount of time, yes. Defining the full scope. And not just the measurement needed right now, but the entire life cycle of that sensor. How it's installed, how it's used, what it needs to withstand over time.
Right.
Only after they have that complete picture do they figure out the best path. Is it modifying an existing proven standard product? Adapting it to meet those specific constraints? Or does the need for, say, novel materials, unique electronics, or completely new geometry mean we have to design something entirely new right from the ground up?
Yep. Okay, that's the key point I wanted to get to. Designing from scratch, doesn't that bring in a whole lot more risk? Longer timelines, higher costs maybe, especially compared to just adapting something that already exists. It feels like a big leap for the customer.
It certainly would be if we were genuinely starting from a blank page every single time. But that risk is really mitigated because we're leveraging, decades of existing proprietary technology and manufacturing know-how.
So it's not truly from zero.
Not at all. While the final product might look unique, the internal building blocks, the strain gauge designs, the material science knowledge, the specific manufacturing processes, those are already thoroughly vetted and optimized from countless previous projects, both standard and custom.
I see.
And that foundation allows us to move relatively quickly into prototyping and validation, even for a novel design. We have confidence that the bespoke solution can be just as reliable, just as accurate as something from the standard catalog.
That transitions us nicely into the technical foundation then, because when you start talking about custom fabrication, maybe exotic materials or complex shapes, how do you maintain that high standard of performance Interface is known for? Custom often feels like it involves some compromise, but for things like aerospace or medical devices, well, compromise isn't really an option, is it?
It's the absolute top priority. There's no room for error. Maintaining that technical integrity is precisely why we rely so heavily on our own proprietary core technologies.
Like the strain gauges you mentioned.
Exactly. We're talking about proprietary strain gauge technology. These aren't components we just buy from a supplier.
And why is that distinction so important? What does having your own gauge tech give you that a standard off-the-shelf one wouldn't?
Control, primarily. We control the entire process, the deposition of the foil, the bonding agents and techniques, the physical geometry, the grid itself down to the micro level. And that level of control is absolutely essential for managing things like temperature coefficients, how the reading changes with temperature. It helps minimize long-term drift, ensures the highest possible signal output for better resolution. All really critical factors, especially when you're dealing with an unusual sensor shape or extreme environmental swings.
So the custom gauge works hand in hand with the custom shape.
Precisely. The other pillar is our advanced machining capability. We need to ensure the metal structure, the flexure, is machined with incredible precision, so it translates the physical force accurately and repeatably to those custom strain gauges. That interaction is the heart of measurement integrity.
So the proprietary tech delivers the performance, but then you need the quality assurance, almost like the insurance policy for the customer, right? I want to touch on that accreditation you mentioned, specifically ISO IE 17025, because that isn't just a basic quality check, is it? It's a specific standard about the competence of testing and calibration labs.
That's exactly right. And for custom measurement solutions, particularly in critical applications, having that WenKino 25 accreditation is, well, it's non-negotiable from our perspective. Operating our calibration lab, the one here in the US under ISO ES 17025.2017, means we don't just claim a measurement is accurate.
You have to prove you're competent to make that claim.
We demonstrate our competence, yes. The accreditation provides proven traceability back to national standards like NIST. It forces rigorous evaluation of measurement uncertainty, understanding the potential error in any measurement, and it ensures that the calibration procedures, even for a one-off custom transducer, are documented, validated, and repeatable, just like they are for a mass-produced standard unit.
So thinking about the client, if they're buying an engineered-to-order solution for something high-risk, knowing that the measurement uncertainty is properly defined and traceable under 17025, that essentially de-risks their operation, doesn't it? They know the foundation they're building on is stable and quantified.
It's really the highest level of accountability we can offer them for the measurement itself. And we pair that with other relevant standards too, like ANSI CSL Z541 1994, which provides a framework for the overall quality assurance in calibration programs. It basically means the engineering rigor we apply during the design phase is matched by the validation rigor in the calibration lab. No weak links.
Okay, let's shift gears now from the lab and the tech specs to the real world. Let's talk about applications, because you often find these custom measurement systems are completely invisible to the end user. They're just working away silently in the background, doing a critical job.
They absolutely are. A really significant part of this custom work involves providing what we call engineered-to-order solutions specifically for OEM clients.
OEM's original equipment manufacturer.
Right. Companies building larger machines or products.
For an OEM, the challenge must shift a bit, right? It's not just about getting one unique sensor for a specific test rig. It's about integrating this custom component seamlessly into potentially thousands of units that are going down a production line.
That's exactly the difference. When we're engineering a solution for an OEM's product line, yes, we're adjusting for performance and features, definitely. But the form factor, how it fits, and crucially, the cost viability become equally critical drivers.
The economics have to work at scale.
They have to. The solution must fit physically within their product, obviously, but it also has to fit economically within their manufacturing budget and final product cost. The ultimate goal is a measurement system that looks, feels, and functions as if it was always designed to be an integral part of their final product, not some awkward add-on bolted on later.
To really make this concrete, you shared a fantastic real-world example that highlights that complexity, the environmental demands, combined with the functional needs. Let's talk about that meat plant example.
Yes, that's a great one. It's one of the clearest illustrations I can think of where customized engineering was purely about solving for survival alongside the measurement need.
Okay, so what was the basic need?
The essential requirement was precise, continuous weighing. A large meat processing plant needed to accurately track the weight of hundreds of trolleys that were constantly moving along an overhead track system.
Okay, so you've got movement, which adds a dynamic challenge to the weighing itself. But the environment in a place like that, I imagine it's pretty extreme.
It is arguably one of the most hostile environments you can imagine for sensitive electronics. Meat processing plants are, by necessity, high washdown environments.
Meaning lots of water, cleaning chemicals?
Exactly. Daily, sometimes even hourly, intense cleaning protocols. We're talking high-pressure water jets, steam, and really powerful, often caustic cleaning chemicals designed to strip away all organic material and completely sterilize every surface.
Right, so a standard load cell or pretty much any normal commercial electronic component would just be destroyed. Corroded, shorted out, drift from moisture getting inside.
Almost immediately, yes. Standard seals wouldn't stand a chance long-term. So the challenge was really twofold. First, the solution had to transmit the weight data reliably and wirelessly. You couldn't have permanent cables that would get damaged during cleaning or snagged by equipment.
Makes sense.
And second, simultaneously, the sensor itself had to physically withstand that continuous, harsh chemical and moisture exposure day after day.
So what did the engineering solution look like?
Well, it involved designing a specialized wireless load cell network. The key was the custom housing and sealing. We had to incorporate specific chemically inert sealing materials, develop extremely durable housings, and design internal component protection potting, conformal coating, the works all engineered specifically to maintain reliable data transmission and structural integrity throughout the sensor's life, despite those relentless high-pressure cleaning cycles.
That's incredible. It's such a clear example of what custom engineering really means. Solving for the accuracy, yes, but also the system integration and the sheer physical survival all at the same time.
It has to be holistic.
Yeah, it makes perfect sense why so many diverse, critical industries end up relying on these kinds of specifically tailored assemblies.
Absolutely. When failure simply isn't an option, standard parts often aren't enough, and customization becomes essential. We see this constantly across aerospace, obviously, where safety margins are incredibly tight.
And medical devices too, I imagine.
Definitely. Medical devices where patient outcomes depend directly on precise control or measurement. Industrial automation, where it might be about process safety or efficiency. Advanced robotics, needing delicate feedback on gripping force, for example. Even heavy equipment, where long-term durability in rough conditions is a key driver for cost-effectiveness over the machine's life.
So if someone listening maybe who is facing what seems like an impossible design challenge right now, something that needs a measurement, but the physics or the environment of your application just seem to defy standard off-the-shelf solutions, what's the ultimate scope here? What kind of help is actually available?
Well, the key takeaway should be that the limitation probably isn't the fundamental measurement technology itself. It's more likely the constraints of the current standardized product catalog. The scope for customization is genuinely vast.
More than just load cells.
Oh, much more. It includes designing entirely new load cells, yes, but also custom torque transducers, complete wireless data acquisition systems developed from scratch for a specific need, complex software integration to make the data useful, and even delivering complete measurement assemblies, fully calibrated and ready to install right into the customer's machine or structure.
And it seems like it all circles back to that core idea that Promise Interface has operated on since way back in 1968. If we can make it, we can customize it. It sounds like it's really about delivering the exact validated measurement solution someone needs, not just trying to sell them what happens to be sitting on the shelf.
That's the philosophy. Custom engineering ensures that the component, which, as you said, is often unseen, buried deep inside a machine, performs its critical function exactly as required, reliably, and validated by industry-leading standards and calibration.
It really raises an interesting final thought for you, our listener, to ponder. When you consider the depth of proprietary technology, the specialized engineering, and that rigorous calibration needed for safety and function fields like aerospace, medicine, automation, how often are these highly engineered, custom engineered to order solutions acting as the silent, completely indispensable foundation for the accuracy and reliability of the technology we interact with every single day, making incredibly complex things seem routine and dependable? Something to think about. Thank you for joining us for this deep dive into the world where measurement goes bespoke. We'll catch you next time.